we've been doing probability. This is the last probability chapter, sort of. We're going to be doing probabilities throughout the rest of the semester, next semester, but it won't be like everything is like a probability question. It's just there's a probability at the end, and there's always a method to get there. So that's not as much as the same. In chapter 14, we just did basic probabilities. In chapter 15, it got more complex. We did conditional probabilities and tree diagrams and that kind of thing. And then 16, we started talking about probability models and random variables. So what we did when we wanted to combine those things. All right. So then in chapter 17, we're going to talk about two very specific probability models. All right. These are ones that are or can be used to answer specific types of questions. So chapter 17 is about the geometric model, which we're going to talk about today, and then the binomial model, which we'll talk about tomorrow and Monday probably. Okay. The geometric model helps you answer questions that you could probably answer without a model. You could still find the probabilities, but then when they get a little more complex, it would just involve a lot of work. And so these models exist, and they exist in your calculator to maybe help you with those instead of having to do a lot of things by hand. All right. So I'm going to open this with like kind of a scenario, and then we're going to do an example, sort of, and then we'll go into what the geometric model is specifically. So remember back in chapter 11, we were doing simulations, and we kept talking about cereal boxes, right? So we had Tiger Woods cards and Serena cards and David Beckham cards in the cereal boxes. We did so many questions with that everyone remembers that question. They know what happened. All right. So in chapter 11, we were asking complex questions that were good for simulations. In this case, though, we're going to change some things, and we maybe could have answered some questions with a probability model instead of having to do a simulation if they were a little bit easier. So for example, you're a huge Tiger Woods fan, and you don't care about completing the whole sports card collection. All right, you don't care about the Serena Williams card. You don't care about the David Beckham card. But you've just got to have that Tiger Woods picture. How many boxes do you expect you'll have to open before you find him? This isn't the same question we asked before, but this situation is simple enough for a probability model. We'll keep the assumption that pictures are distributed at random, and we'll trust the manufacturer's claim that 20% of the cards are Tiger. All right? So when you open the box, the probability that you succeed in finding Tiger is 0.2. And now we'll call the act of opening each box a trial. So there's a few things happening. Note, there's only two possible outcomes now. Yes, there's 3 cards, but I don't care about the other ones. So it's either I succeed and get a Tiger card, or I fail because I don't. All right, so there's only 2 possible outcomes that I'm really concerned about. You know the probability of getting a Tiger card is 0.2, so you know the probability of success, which means you also know the probability of failure. If you can get a Tiger card 20% of the time, then how often do you not get a Tiger card? 80% of the time. And then as we go through this, we're going to assume that each cereal box is independent, right? Okay. So finding Tiger in the first box doesn't change what might happen when you reach for the next box. We can talk about that a little more, talk more about independence. But for now, we're just going to assume they're independent. So before, if we were going to do a simulation of this, we were trying to get a Tiger Woods card, the first one. We just wanted one Tiger card, right? If we did a simulation, we would assign random numbers. So I would assign like 0 and 1 to Tiger because that's 20%, and then 2 through 9 to not Tiger because I don't really care what the other ones are, right? And I would want to simulate numbers until I got a Tiger Woods card. So I would generate random digits until I got the first Tiger. Now, that could vary quite a bit, right? That could vary because I could have drawn a Tiger Woods card on the first card. Could have been on the second. On the third. All of you guys could have done different simulations and got different results. Okay? Now we know some stuff about probability models. We could start making a probability model of this, maybe. Okay? So if I wanted to know how often or when probably I get my first card and how many boxes, that might look something like this. So maybe I get a Tiger Woods card the first try, right? What's the probability of getting a Tiger Woods card? 0.2, 20%. Maybe that doesn't happen. Maybe it takes me 2 boxes. Well, that means I didn't get a Tiger Woods card, and then I did. Right? And then I didn't get a Tiger Woods card, but then I did. Right? Now we have to continue this, and there really isn't some necessary endpoint, right? There isn't a specific number of cereal boxes to which we would get the first one. Like, it could be infinite, correct? So with this idea in mind, this is kind of what the geometric model is helping you to achieve, all right? It's helping you to figure out what the probability of getting the first something is in a specific number of trials. All right, it's going to give you a specific number. So what's the probability that you get the first Tiger Woods card on the 4th cereal box? Or what's the probability the first Tiger Woods card on the 7th cereal box? Okay, if we're doing flipping a coin or something, what's the probability you get the first heads on your 5th flip? Okay, the geometric model is going to help you kind of figure out what's happening in a specific set number, right? Because here, if we try to do this probability model, it could keep going. But it uses the same idea. There's 2 outcomes. Each trial is independent of the X, right? And there's success and failure. There's only 2 possible probabilities in the setup of the question, right? So because of that, we have our binomial model tomorrow and the geometric model today are all based on what we call Bernoulli trials, right? And a Bernoulli trial is a fancy name for what we just talked about. Bernoulli trial is a trial that has 2 outcomes only. Now, it might seem like it has multiple outcomes, but we're only concerned about one, so we only have 2 outcomes. For example, if you're rolling a die, there's technically 6 possible outcomes, right? If I'm looking for 5 specifically, then there's only 2 possible outcomes. There's a 5 or not a 5. That's all I'm worried about, right? So that would be 2 possible outcomes. So Bernoulli trials have 2 possible outcomes. Each trial is independent of the next. And you always have, you know the probability of success and you know the probability of failure. We call the probability of success P. And then our book uses the probability of failure as Q. The AP people think of Q as 1 minus P because it's the complement. So if you see 1 minus P, that's the same thing as Q. All right. But so Bernoulli trial has 2 outcomes that each trial is independent, and you know the probability of success and the probability of failure. Right? It's a specific definition that we're going to use to build our model in a second. So just in case, we're going to go through and decide if these are Bernoulli trials or not. We're going to do the first 3. We'll do the other 2 tomorrow when we talk more about independence. Okay? So the first one says, we roll 50 dice to find the distribution of the number of spots on the faces. In that case, are you looking for 2 specific outcomes? No, you're looking for all 6 of the outcomes. So that would not be a Bernoulli trial. Does that make sense? On B, how likely is it that in a group of 120, the majority may have type A blood, given that type A is found in 43% of the population? Are there 2 possible outcomes? Yes, because I'm only worried about type A or not. Right? Yes, there's other blood types, but I'm only worried about one of them. So it's either I get type A or I don't. Do we know the probability of success and failure? We know the probability of getting type A person. 43%, right? So then I could find the complement for what it would be for not type A. So I do know the probabilities of success and failure. If you have 120 people, it's just saying 120 people. It's like in a majority, like in a group. It doesn't say that they're related or anything. Would you assume that the 120 people are independent of each other? Yeah. There's no reason to think they aren't. Okay? If it was a room full of family members, that would not be independent because, right, blood type is genetic. But it doesn't say that, so we're assuming they're independent. And then C, we deal 7 cards from a deck and get all hearts. And how likely is that? We have 2 outcomes, hearts or not, right? We know the probability of getting a heart, but is drawing 7 cards from a deck independent event? No, if we don't replace them and we keep drawing them out, they're not independent, right? And it says we deal 7 cards. So you're getting all 7. So you've reduced probability each time you draw a card, right? So those are not independent events, so not Bernoulli trials. Okay? So all the things we're doing with the geometric model have to have Bernoulli trials. That means they should be pretty straightforward then, right? If every single instance we're talking about then with geometric model has 2 outcomes, and we know the probability, and they have to be independent, then it couldn't be anything too complex. Does that make sense? So I don't think the geometric model is that bad. Okay? So here is the geometric model. It tells you the number of trials until it gives you the number of trials for the first success, and it gives you the probability of that happening. Right? It is always about the first success. Always. It's going to say what's the probability that you make your first free throw on the 8th shot. What's the probability that you roll a 3 for the first time on a die on the 10th roll? Okay? It's asking you specifically the first instance of something occurring. That's very important. So when you do the binomial model tomorrow, that's how you're going to differentiate. All right? When the questions are being asked, they're going to seem similar, but if you're looking for the first something to happen, then you're only looking at geometric model questions. Okay? This is how we notate the geometric model that we're using it. Just like back in the day, we used the normal model. We said we were using n, normal, with a mean of this and a standard deviation of this. All right? That just told everyone we're using that model. In this case, if we're using a geometric, we just say we're using geom of whatever our probability of success is, if you're going to get all notationally about it. Most of you guys are going to ignore that part. But if you look at my homework, that's what you're going to see. Okay? So here is how you would calculate all these probabilities. Again, if x is the number of trials until the first success occurs, then you have q to some power times p. This is all that means. I did 2 examples up here. The probability that my first tail on a coin is on my 7th flip. What's the probability of getting tails on a coin? 50, right? So I didn't get a tail, so the complement is also 50. Didn't get a tail 6 times, and then I did, right? So coins are technically Bernoulli trials, because you have one or the other, right? And then you have probabilities, but they're all the same, so you're like, okay, well, that's not really a big deal. That's 0.5 to the 7th power. Why are you going to separate it? Well, then what happens with dice? Probability that my first 5 on a die was rolled on my 10th roll. That's a Bernoulli trial because I'm only worried about 5s, right? And they're independent each roll. We know the probability of getting a 5 is 1 out of 6. And so we know the probability of not getting a 5 is 5 out of 6. So if my first one comes on my 10th roll, that means 9 of them were not 5s. And then I got a 5. That's all this formula says. Right? So it says the probability of failure to the number of trials minus 1 power times the probability of success. That's really fancy. You could do that without the formula. Probably would be more confusing if you tried to use the formula. You just know what it's supposed to be. Right? You don't get it, then you do. Right? Because it's a probability model, you can find a mean and standard deviation for a probability model, right? We can find the expected number of trials it would take for something to happen. So, the expected value will tell you how many trials you would expect before the first success. So, for example, let's say we're doing this whole die question, all right? I want to know how many rolls it should probably take me on average to get a 5. Okay? What's the probability of getting a 5? 1 in 6. So you would do 1 divided by 1/6. And so what's 1 divided by 1/6? 6. So I would expect my first 5 to come by the 6th roll. Does that make sense? Mm-hmm. So the expected value tells you how many trials do you expect before the first. So if I want to know, not necessarily a probability, I just want to know how many rolls I would have to roll on average to get a 5. The probability of getting a 5 is 1 out of 6 on a die, right? So we would do 1 divided by 1/6, which is 6. So I would expect it would take me 6 rolls to ensure that I got the first 5. Okay? Now, that is not on your AP formula sheet, this formula, 1 over P. But I guarantee that they will ask you about this. If they're doing a geometric question, they're going to ask you about the expected value. So you're going to have to know that. Now, because there's an expected value, there's also a standard deviation. They like hardly ever ask you about that with geometric. Okay? So you can write it down, and you can use it if they ask you in the homework, but that's probably the only time you're ever going to see it. Okay? Your binomial model stuff that we're going to do tomorrow, it's all on the formula sheet. Okay? So really this is what you have to remember. As expected value for the geometric model is 1 over P. Okay? Yeah, maybe. How about we do some actual examples then?
All right, let's do it.
Know that it's there. Just know that standard deviation, that formula is there in your book if the book asks you, but I have never seen it asked anywhere else because it's not on the formula sheet and they're not going to make you memorize it. All right, so here we go. Now, some of these, this first example I'm going to do, we can do it by hand. It's not a big deal. But then on the next example, I'm going to show you how you can use your calculator because some of them get lengthy and you don't have to do them by hand. All right, so a basketball player has made 80% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game he, and there's some scenarios. So just so we are all on the same page, he makes 80%, which means he misses 20%, right? You have to make sure these are Bernoulli trials before you do anything. Do you have 2 outcomes? Yes, making them and missing them. Do you know the probabilities of those happening? Yes. And we're assuming that the shots are independent. So we have Bernoulli trials, so we can use this whole geometric idea. So A says you missed for the first time on the 5th attempt. So if you're missing for the first time on the 5th attempt, how am I going to calculate that? You miss, yes, you miss for the first time on the 5th attempt. So that means you make 4, and then you miss 1. I'm not going to calculate that at the moment because I don't want to type it on my calculator, but we could do that, right? Okay. On B, he makes his first basket on his 4th shot. So what about that one?
0.2 times.
Right. That means he misses 3 and then makes 1. No big deal. On C, makes his first basket on one of his first 3 shots. So in this case, we would have to do, what's the probability that he gets his first basket on the first? What's that probability? 0.8. Plus the probability that he gets his first basket on the second. That's 0.2 times 0.8. Plus the probability that he gets his first basket on the third. Right? So you could do that by hand. But in this case, this happens to just be a short one. Generally, they're not that nice. They say, what's the probability he makes his first basket on the 11th shot? Well, just gets lengthy trying to write that all out and do it all. Okay, so that's where your calculator will help you, and I'll show you that in a second. Okay, because no one has time for that. No one's going to write that all out. It's not going to happen. Okay. 11 says, for the basketball player in exercise 9, what's the expected number of shots until he misses? So the expected number of shots until he makes the first miss. Remember, the expected value for a geometric model is just 1 over P. P is the probability of whatever we're trying to get first happening, right? So first miss. So what's the probability of a miss? 0.2. So we would do 1 divided by 0.2. So what's 1 divided by 0.2? You guys need to decide. Is it 5 or 20? Sorry, man. Sorry, man. So close. Oh. All right. So, questions about those questions. No big deal, right? You could do those, no issue. I'm going to do one more example, and we're going to use your calculator to do it. So I'm going to give you the reference sheet for the calculator, and then I will talk you through it, but this is just for you to have so you know what's going on. All right. So on here, it tells you about the geometric model in your calculator. Clay, you have a fancy calculator, so wherever you go to find normal CDF is going to where this is. All right, so there are two actual functions we're going to use. So if you go to second variables in your calculator, second variables, second bars.
Oh.
You need to scroll, if you're on an 83 or 84, you need to scroll up, because if you scroll down, it's going to take you forever. So scroll up, because it's the last two listed. Geometric PDF and geometric CDF. Everyone see those? All right, now these, we will actually use both of these. When we do normal stuff, we don't ever use PDF, right? Geometric, we're going to use both. But they have very specific functions. You need to make sure you listen very carefully. All right? I'm actually going to go back to the hoops question to explain. Geometric PDF gives you something if it's asking a specific question, like A and B, right? The first thing happens on this specific trial. That's what PDF does, okay? So, for example, if I was going to answer A misses for the first time on his 5th attempt, T is the probability of whatever you're doing first on that attempt. So misses is P, because we're trying to miss on the 5th attempt. All right, so missing was 0.2, and then X value is how many attempts? So 5, and it calculates that for you. If you don't have an 84, you have an 83, you would just type in the probability, comma, the trial. Okay, yeah? And that should be the same as if I did 0.8 to the 4 times 0.2. Okay, so PDF will give you something very specific. CDF, on the other hand, has the same exact menu, so you have to be really careful that you know which one you're using. CDF, see, it looks identical, so you got to be careful. CDF, though, the C in CDF stands for cumulative. So that means it's going to add things for you. All right? So CDF will answer questions like C, where it says makes his first basket on one of his first 3 shots. It will do all of those for you and calculate them all together. All right? So again, P is whatever your success is. In this case, we're making a basket for the first time. So in this case, making a basket would be P, so that's 0.8. And your X value then is the number of trials, and it'll go back through and add them all together. It won't just do 1. It'll do 1 and 2 and 3. Okay? So 3 trials. And again, if you added all these up together, that's what you get. Okay? Does the PDF and CDF difference make sense? All right. So let's quickly do another example, and then I'll give the assignment. It says only 4% of people have type AB blood. So on average, how many donors must be checked to find someone with type AB? So this is asking to find someone. That means find the first person. Right, that's important. Find the first with type AB. So we got to make sure it's Bernoulli trials before we can do geometric model. Do you have 2 outcomes?
Yes.
Yes, AB or not. Do we know the probability of getting AB?
Yes.
Then we know the probability of AB not. So that works too. And then we're going to assume these people are independent. So we can use geometric stuff. So how do I find an expected value for a geometric model? 1 over P. And in this case, P is success of getting type AB. So 1 divided by 0.04. So what's 1 divided by 0.04? What? Thank you. Well, I was hoping for Min to say something crazy. Okay, checking. All right, so on B, it says, what's the probability that there is a type AB donor among the first 5 people checked? That means 1, the first one in the first 5. So if we're doing the probability of the first one in the first 5, then what are we going to do in the calculator? Because I don't want to do it by hand. We're not doing normal anything, so incorrect. Geometric CDF, our probability of getting a type AB person is 0.04, and we're using 5 people. So that's going to add up the probability of it happening on the first person, and the second person, and the third person, and the fourth person, and the fifth person. So we get 0.18. Questions about that? C, what's the probability that the first type AB donor will be found among the first 6 people? So same thing, what was the only thing we're going to change? Yeah, the number of trials, X value, 6. And that adds them all up together, so 0.217. Now D, a little tricky, so you think about it. It's not that bad, but just a little different. What's the probability that we won't find a type AB donor before the 10th person? So that means we want to find the first person 10 or later, right? Does that make sense? I want the first person to come the 10th or later. Our calculator only does from like 0 till up to a number. It doesn't do like something and greater, okay? So we're going to have to subtract from 1. Does that make sense? We'll have to do 1 minus the probability that the first person comes in the first 9 people. Does that make sense? If we want them to come 10 or later, then we have to subtract out everything before. Does that make sense, everyone? All right, so we do 1 minus geometric CDF, still 0.04, but this time 9. So 0.692. Questions about that one? That was a little bit different. Because it says before the 10th person, so we want to have the 10th person included later, so we're just going to go up to 9. Questions on that one? All right, that's the geometric model in a nutshell.